Is it recording? Sorry.
Yes.
Okay, now it says dismiss. Okay, great. Okay, so welcome everyone to this week's APRG seminar. We are really glad to have Greg Knese from Bristol, and he will talk about the local theory of stable polynomials and bounded rational functions of several variables. Over to you, Greg.
All right. Thank you very much. Thanks so much for the invitation. It's a pleasure to speak to you all. I was fortunate to be able to visit IISC in 2013, so I put a couple of my photos into my slides just for fun, and you can, I don't have very good photos, but you can try to guess where they are. So this talk...
Was that for the iVota?
Yes.
Okay.
Yeah. So this talk is about a recent paper with Kelly Bickel, James Pascoe, and Alan Sola, and it's kind of a long paper, so I have to kind of pick a certain thread running through it, and so that's what I'll try to do. But first, I'll give a bit of an overview. So first, let me just start out with the basics. So stable polynomials are a fundamental concept. There's nothing deep about the definition, but they seem to be turning up all over the place in different areas of math and areas connecting different areas of math. So a stable polynomial, I'm going to stick with just a certain, I guess, category of these. So it'll just be a polynomial is stable if it has no zeros in the product of upper half planes. So this is just the upper half plane inside of C, and I'm looking at upper half planes in the product of upper half planes in CD. And so you can consider variations on this definition, like you can consider polydisks, or you consider closed upper half planes and all sorts of different things, but this is just what I'll do for now. And just some key examples to start out are this first polynomial, z1 plus z2 minus I, z1, z2. It has no zeros in the product of upper half planes, which you could just check. It's not obvious from the definition, but you can do it. And one thing I'll be focusing on a lot in this talk is boundary behavior. So they don't vanish on the product of upper half planes, but we are interested in polynomials like this that do have zeros on the boundary or on the distinguished boundary, which in this case will be RD. So it's like we have the upper half plane up here, or we have a product of upper half planes, and we're interested in the case where we do have zeros on the boundary or distinguished boundary, RD. And so this polynomial here just has a single 0 in R2 just at 0, 0. Whereas here's another example of a stable polynomial, just z1 plus z2, which this is stable that's easily seen because in the product of upper half planes, this has a positive imaginary part. But in R2, it has a whole line of zeros. And so this will be something I'll introduce in a moment, that there's this kind of dichotomy. There's like two types of stable polynomials, basically. And here it is. So here's my first photo too. This is, everybody probably knows what this is, I guess. This is Mysore Palace. So here's the dichotomy of stable polynomials. First, I need to define the reflection of a polynomial in the setting of the upper half plane. So that's just where you take the conjugate of the coefficients, but you can write it this way, where you take conjugates of variables and the conjugate of the whole polynomial. And so the two types, one of
I
these
think we have
names is a.
good. Can we have a question from the audience if she can ask?
Sure.
Yes, there is a disk version also. Will you be considering that as well?
The disk version.
Oh, I decided to just focus on upper half plane for this talk.
Okay, thank you, thank you. And it has applications in tensor product and entangled states, quantum entangled states, stable polynomials by Wagner, and we can put them in tensor product form also, and then applications to quantum entanglement.
Oh, okay. Yeah, so in the associated paper, we do have this a bit of a back and forth between upper half plane and disk versions of stability. Just, I think this talk runs smoother if I don't talk about that too much, just because that's not the exciting part, maybe, to me. So, but yeah, okay. So the real stable is a much more common notion, and that's when a polynomial has all real coefficients. So that would be p equals p bar. We allow a little extra flexibility in this, where you let it be a multiple of its reflection, and just call it real stable in that case. And then here, pure stable is, I don't think this is a common name. I don't know if there is a common name for this concept. I've seen things like scattering stable, but it's just when P and its reflection have no common factors. And these two types play, so I'm going to be studying bounded rational functions, and it turns out pure stable polynomials will be denominators of these, but real stable polynomials come up too when we look at level sets of certain rational functions as well. So both of them come into it. A proposition that's not too hard to show is that any stable polynomial factors into a pure stable piece and a real stable piece. So you can, it's not too hard to see that you take P and P bar and you pull off any common factors, and then you have to show that their common factor is real stable, and then the thing that that's not in common ends up being a pure stable factor. Okay, and so this talk is about using stable polynomials to study bounded rational functions. And so I guess the definition there is pretty self-evident. It's a rational function on the product of upper half planes, let's say, that maps into the unit disk, for instance. And so it'll be two polynomials, Q over P, where P is stable to make it analytic. And then a very special class of bounded rational functions are the so-called rational inner functions. And they satisfy this condition that on the distinguished boundary, the modulus of Q equals the modulus of P. And so that's just to make it so that Q over P has modulus 1 almost everywhere on the distinguished boundary. That's the usual definition of inner from classical function theory. And then there's a theorem of Rudenstaut, usually stated in the polydisk setting, but you can say it here, that a rational function is a rational inner function if and only if it's of the form P bar over P, and we also allow this constant in here to have modulus 1. And this is a very special class of bounded rational functions, but it's also important for other reasons, because it's like dense locally uniformly in the space of all analytic functions from the upper half plane to the disk. So you can locally uniformly approximate these functions with rational inner functions. And there are also generalizations of finite Blaschke products, which makes them interesting as well. And so some of the problems that we've studied in this paper and also in previous papers are existence of non-tangential limits at the boundary of these functions. You could, of course, study these issues for just analytic functions in general, but rational functions make it, you know, an interesting mix of algebra and analysis. We've also looked at descriptions of boundary level sets of these functions, and then an interesting problem that maybe I didn't realize was a problem until recently is describing numerators, and I'll state this more formally later, but the question that we'll talk about is basically given a stable polynomial p, describe all q such that q over p gives you a bounded rational function. And I'll basically restate this later in a local setting where I'll look at this in two variables, and we'll focus on a single zero, and we'll want to see when is q over p bounded in a neighborhood of 0, 0 intersected with the product of upper half planes. But these are the basic questions that we looked at. And to address these questions, we came up with a way to kind of divide it into sort of three tools. So stable polynomials have special homogeneous expansions. So there's some interesting things you can say about their homogeneous expansions. Let me just try to briefly say it because I didn't want to go too far down this path, but I can write out P in a homogeneous expansion. So let's say if it vanishes to order m at 0, 0, I can write it out starting with a homogeneous polynomial of order m, and then I have higher order terms. And then it turns out this first term is actually stable itself, but it's homogeneous, so it ends up being real stable. And that means you can multiply it by a constant to make it real. So if you do that, like multiply everything through by a constant, then you get this interesting property that, let's see if I write out a p in terms of its a polynomial whose coefficients are the real parts of p's coefficients, and a polynomial whose coefficients are the imaginary parts of p's coefficients, then you get that I can arrange for it to start out with the first homogeneous term of A, and then B has no mth order homogeneous term. And then there's some other interesting things you can say about the next term, like this term has to be here, and AM over BM plus 1 has to be what's called a pick function, and has to map into the upper half plane. Anyway, I didn't want to say too much about this, but there's a lot of interesting things you can say about just homogeneous expansions. And that's the basis for one of our first theorems, which I just wanted to state. I'm not going to prove this today, but which we showed that given a bounded rational function from the product of upper half planes and just normalized to map into the unit disk, it turns out it has a non-tangential limit at every point of Rd. So these functions can have singularities at the boundary, but the singularities don't matter when you're considering existence of non-tangential limits. So that's interesting. This was earlier proven in a paper of mine just for rational inner functions, but it's a little surprising that it pans out just for all bounded rational functions. So what our first tool leads to this first theorem and some related results about non-tangential regularity. Our second tool is what I'll try to focus on today, and this is the part that excites me a lot, but it does, get a little technical later. So I don't want to scare anyone, but it gets a little messy. But I'll try to do my best to explain it. So the Puiseux factorization theorem that I'll present lets us do a bunch of different things. In particular, talk about this admissible numerator question that I mentioned. We can characterize admissible numerators for many cases, and there's also lots of other interesting stuff we can do with it. And it's also related to describing boundary level sets for rational inner functions and just general bounded rational functions. This general case is actually handled with a totally different tool, which is closer to, I guess, some papers by Bickel, Pascoe, and Sola, where they use operator theoretic formulas to study behavior, like not, I guess we call it ultra tangential behavior. It's like behavior on the boundary, as opposed to what's sometimes studied is the non-tangential. So the boundary level sets is the non-tangential behavior. And you can study that with some operator theoretic formulas that people may have seen, like transfer function formulas. And there's just some things you have to do to get transfer function formulas from operator theory to work well at kind of an isolated point. Okay, and I wanted to say a little bit about boundary level set descriptions here, just because there's some interesting pictures I can present. So our Puiseux factorization theorem makes it possible to describe what the boundary level sets of rational inner functions in two variables look like. And I think it's interesting just to present kind of this picture to sort of show you what's happening. So the idea on this page is I have a rational inner function here. So that's p bar over p. Let me try to zoom in on this for a second. And I'm looking at the set where it's equal to e to the I theta. So on the boundary, it's equal to unimodular complex numbers. It's helpful to rewrite this level set in terms of its real and imaginary parts of P. So if I rewrite capital A is the real part of P and capital B is the imaginary part, these level sets turn out to be level sets of a whole family of real stable polynomials, actually. So this whole family A plus TB, where T is a real number, gives you a whole family of real stable polynomials, and their level sets, as you vary T, give you the level sets of the rational inner functions. And one interesting thing from our Puiseux factorization theorem is that if you look at these polynomials at a boundary 0, which we'll take to be just the origin, just without loss of generality, their 0 set description, you can have several branches, but the branches all break up into smooth pieces. So you can basically locally factor it into smooth branches, which is not what ordinarily happens with just a general polynomial, that you can't just break it up into smooth pieces. Like if I'm trying to factor like z squared equals z1, and I'm trying to do branches parameterized by z1, well, you'd have two different branches of square root or something. So that situation does not arise for boundary zeros of real stable polynomials. And so you get, when you're looking at these different level sets, you get whole families of of curves, and so you get smooth branches. That's one interesting property. As I mentioned in the previous slide, in the homogeneous expansions stuff, I can arrange for the imaginary part to vanish to a higher order. So it has, it's actually just one more higher order. So it has more branches going through a boundary 0 than all of these other real stable polynomials. And so I've drawn, just what the pictures usually look like. So B's level, so B equals 0, which does correspond to one of these level sets up here. I've drawn it with the dashed line. Here, B has 3 branches going through the origin. All of these branches have to have negative slope, is something that happens in these pictures. So they always have negative slope. And then the different branches, since they're level sets, they have to interlace. I mean, to get from one level set to another, you have to like run through all of the values by continuity at places where there isn't a 0. So this picture is roughly what the graphs look like if you try to look at various different level sets. So so B's branches here are these dashed lines, and these dashed lines are helpful in kind of, they're used to trap the other branches in between them. So if I try to draw some other level sets in here, I get, well, maybe I'll have these pink curves in here, but they'll be in between the level sets of B. And you might have like separate level sets that are kind of out here, but if you zoom in into a smaller box, you won't see these later level sets out here. And so this is roughly what the pictures always look like. The curves form these like bundles in between the branches of B, and everything has to have negative slope, so it ends up always kind of looking like this. And so our Puiseux factorization theorem for real stable polynomials gives us this pretty complete picture of what boundary level sets for rational inner functions look like, and also what boundary level sets just in general for real stable polynomials look like. Okay, so let me, without further ado, present something pretty technical, but gets to the heart of some of the most exciting stuff in the paper that I'm talking about. Let's see, so this, just for setup, let me mention some standard facts. So to start out, let's just take a polynomial for this little box here. It doesn't have to be stable. Just some standard introductory, like algebraic geometry or algebraic curves will say that you can apply the Weierstrass preparation theorem and factor P. So this is the Weierstrass preparation theorem. Locally, I can factor P into a unit. So here U belongs to the set of convergent power series. Let me do smaller writing. So this C with the curly brackets is the ring of convergent power series centered at 0, 0. So we can factor P into a convergent power series that doesn't vanish at 0. And so this is a unit in that ring. So that's the part you don't care about. And then the rest are these Weierstrass polynomials, which part of the definition of a Weierstrass polynomial is that it's a polynomial with respect to Z2, but then its coefficients are convergent power series with respect to Z1. And you could do it in the other variables switched, obviously, and there are other properties, but it'll be a product of these things, and you'll assume that each P1 is irreducible inside this ring. And then you can go further in two variables and use like the Newton-Puiseux theorem, which lets you factor the irreducible Weierstrass polynomials into these pieces involving Puiseux series. So that's series involving fractional powers. And so if people aren't so familiar with this, you'll be forgiven, because I didn't know a lot about Puiseux series, until 10 years ago or something. But just in general, we can factor each one of these into, say, z1 minus this analytic function, and we have to throw in all different branches of z1 to some fractional power. So there's a lot going on here, but it's basically another way to write it is that we parameterize the curve associated to Pj via this map. So the zero set of Pj is described by points of this form. We can write it in this factored form by writing out all different branches of z1 to the 1 over some power. Okay, so this is just some general theory. And the thing I want to tell you is that for stable polynomials, you get a very special form for these analytic functions that tell you exactly what stable polynomials look like near a boundary 0. So here's that portion of it. So if I have a stable polynomial in two variables, I should emphasize that, two variables, then this Pj that appears in the Puiseux factorization, which you can use to parameterize locally the different branches of P, has one of the two following forms. It's either real stable or pure stable. If P is real stable, then it only has real stable factors. And if P is pure stable, then it only has pure stable factors. So here's what the real stable case looks like, and it's the easiest one to state. This is the smooth part. All of the branches are just analytic, so there's no fractional power series necessary, and the negative of the phis, I'm just trying to write things in a positive way, trying to stay optimistic. The negative of the pj's have real coefficients, so the aj's, the coefficients here are all real, and the first coefficient is positive, and so you're basically writing out, if you have a real stable polynomial, it basically factors locally into a bunch of pieces of this form, where this, sorry, I took away the minus sign. I'll write it like just with a different function. So gj is just negative bj, and this has first coefficient positive, and that's what gives the negative slope property on the previous slide. So so everything here, all real stable polynomials, they always have negative slope. I mean, I guess they can have zero slope. I left out the case. You can get horizontal and vertical lines, but ignoring that, the slope is always negative in those pictures on R2. And okay, and then here's the pure stable case, which is, it's technical, but it's technical because it has to be, and that's maybe the interesting part about it. So again, I'll state it in terms of what negative Pj looks like. And so I'll try to walk people through this who are interested in some of the details. So in this Puiseux factorization, it's basically, you start out looking like a real stable polynomial. So this part Q is a polynomial with real coefficients. And so you go along with real coefficients, and it starts out looking a lot like the real stable case. You have, well, its value at 0 is 0, but its first derivative at 0 is positive. And so again, it's almost like you have negative slopes in the pure stable case, even though the boundary 0 sets there don't have to be curves or anything. So you start out looking real stable, but then eventually you hit a point where you get a complex coefficient. And the place where you hit a complex coefficient, there's extra details here, like the first complex coefficient here has positive imaginary part. And that actually is like an important property of making it pure stable. So that will like force it locally to not have zeros in the product of upper half planes. And there's other properties here that the first place it occurs is at an even power. And so there's all this data involved, and it does look quite technical, but it does play a role in what I'm going to say about these other questions. So I'm not going to expect anyone to memorize this, so I'll try to keep it running on different slides, but it does end up letting us do a bunch of different things. So okay, so now the next thing, I'm just going to kind of rewrite this theorem in the pure, rewrite just a theorem, I guess, which I'll call the pure stable factorization theorem, just to write out all of this detail. So the pure stable factorization theorem, I'll separate it out into the factorization and all the data required. And this is just like a restatement of what was done in the pure stable case on the last slide. So I have P with a 0 at the origin, which is pure stable. And so it factors into all this stuff from the last slide. So you have the Weierstrass factorization and then the Puiseux factorization, but we've described what the Puiseux functions look like. And so they all have this form here. And so the data involved here is that, again, you have this real polynomial. So that's this here. I have a bunch of real polynomials with kind of a, so I call these like the initial segments of the branches. So these are how the branches start out, with these real pieces. And then they stop somewhere. And so these 2Ls are what we've often called cutoffs. We've also called them contact orders because you can use them to measure kind of how at what rate the zeros of P tend to the boundary asymptotically. So cutoffs or local contact orders. And so these initial segments have to behave like the real stable case. So again, they have to have this like positive first derivative. And then we have this Puiseux series part here. So I've tried to write it separately right there. You have to multiply over all branches of plugging a fractional power into some analytic function. And so here are these analytic functions appearing there. And they start out, this is the first place where you get a complex coefficient, and it has to be with positive imaginary part. Okay, so so this is the pure stable factorization in all of its glory. One thing I don't want to in case I run out of time, maybe I'll just mention that it's something that we've shown. I'll state this later, but I think now's a good time to do it also. That it turns out that if you cut out all of the Puiseux series from this formula and define a polynomial like so, I replace all of this nastiness with Puiseux series with just I. So I'm going to write. So I have to include these initial segments, but if I just replace all of the Puiseux series just with the imaginary number I and include things to their right multiplicities, I define this polynomial P bracket, and a theorem I'll state at the end also is that if you write down this thing, which, this won't be a stable polynomial in general, but it'll basically be locally stable. So it'll have no zeros on the product of upper half planes intersected with a neighborhood of 0, 0, but it'll also have the property that P divided by bracket P and bracket P divided by P will be bounded on a set like this. So the upper half plane intersect a neighborhood of 0, 0. And so you take all this data involved in this complicated factorization, and you can basically reduce most questions locally to studying this easier polynomial because P over bracket P and bracket P over P are bounded. So I did want to mention that because this is a nice simplification that occurs. Even though you have to go through all of this, you can kind of cut out the Puiseux series at the end. And I don't see any way to kind of avoid the Puiseux series just altogether and jump to these polynomials from the beginning, because you have to get to these segments and cutoffs somehow, because this is the really important data involved in understanding what the stable polynomials look like locally. Okay, so now let me state the question, which we didn't realize was such a deep question until recently, the admissible numerator question. So given a pure stable polynomial P with a 0 at the origin, I guess this is the local admissible numerator question, for which Q is Q over P bounded on the upper half plane, the product of upper half planes intersect a neighborhood of 0, 0. And so if you can solve this locally, then you can solve it more globally by just, if I have a pure stable polynomial, I look at I just look at its boundary zeros, and pure stable polynomials have isolated boundary zeros. So you can just go around to each boundary zero and study this question locally, and then try to synthesize your answer. But here's kind of our local study of it. We define this ideal, so just define the set of all polynomials Q such that this holds. So Q over P is bounded on product of upper half planes intersect this neighborhood. And let's try to, so the question is, describe this ideal of admissible numerators. And let me mention the easiest thing. Here's an easy inclusion. So we already know that, P has to be in here because P over P is 1. P bar has to be in there because P bar over P is this rational inner function that I've mentioned. So then the ideal generated by P and P bar has to be inside here. So that's an easy direction. And, you know, at first, when we studied this, we thought, oh, we have an answer. It has to be the ideal generated by P and P bar. And it turned out that that's actually true in a kind of a generic case, which is nice, but also generic and special. If P vanishes to order 1 at 0, 0, then you do get that this ideal is just the ideal generated by P and P bar. And I think I have a couple examples to illustrate it and to illustrate some of these theorems. So let's take this first example that was presented. So Z1 plus Z2 minus I, Z1, Z2. It's not often that you can find a Puiseux factorization for a polynomial, because sometimes you need something like the inverse function theorem to write it out. But for this one, you can actually factor out the right unit. And I can write this as Z2 plus this function of Z1, and then you expand this part. And oh, I wrote this wrong. In this case, the Q, so the initial segment, ends up just being Z1. So it's a pretty simple example. And you go along in the power series, and just at Z1 squared, you get the first complex coefficient occurring at an even power. And so this is the data here. You have like the initial segment, there's just 1. The cutoff is at 2. And then we have this function C that describes the rest. The ideal of admissible numerators is just the ideal generated by P and P bar, which if you play around with P and P bar, you can show that it's the same as the ideal generated by Z2 plus Z1 and Z1 squared. So it's a pretty simple ideal, obviously. You get polynomials that, well, they have to vanish at the origin. And then what's, you know, the non-obvious condition is that since they're generated by this polynomial, that they're in their homogeneous expansion, they sort of, F would have to start out as something like a coefficient times Z1 plus Z2, because I need these two partial derivatives to be the same. And then basically after that, it's unconstrained. So after that, I could have this F2 has to vanish to order 2. So the main condition to belong to this ideal is that that its first homogeneous term has to be this, or in other words, it has to match the first 2 partial derivatives. All right, and then here's a slightly more complicated example. I don't know, I'm running out of time, so maybe I won't go through it, but this one vanishes to order 1 as well, but you get slightly more complicated ideal in the end, but looks roughly the same. And so this talk goes for 50 minutes, is that right? Or?
No, 60 is fine. I mean, yeah.
Oh, okay. I mean,
yeah.
If people are,
we
usually go for
60 anyways. I mean, including questions, maybe we can stop at 55 or something.
Oh, okay. Yeah, that's fine. Let's see. So I could go through a little bit of proof of this easy inclusion, because it does show a little bit of what goes on in some of these proofs. Maybe I'll come back to it if there's like tons of extra time, but I'm sure I can take up the rest of the time just blathering on the better conjecture. Okay, because this is kind of a busy slide, but it's also, I think, interesting. So here is just, all of this is just a recap of the pure stable factorization to have it handy. And to get a better conjecture than that easy inclusion that I mentioned, let me state a theorem that gets us, the idea, I guess, the strategy is to describe this ideal of admissible numerators, so the Q's such that Q over P is locally bounded, basically, by trying to describe as big of an ideal sitting inside it as I can, and then eventually showing that it's everything. And so we can show that this ideal here, built out of all of this complicated Puiseux factorization data, lives in there. So you take these initial segments and these cutoffs that occur in this data, and this ideal appeared just in that example I presented. So Z2 plus Q, comma, just a power of Z1. And so I take the ideal generated by those two, and then the product ideal MJ times generated by those, which is the M's were these multiplicities associated to things. And then you take another product ideal of that. And so that's complicated, but it turns out that this is a pretty big ideal sitting inside of this ideal of admissible numerators. And we conjecture that they're actually equal. And we have some pretty good evidence of that. So first, here's just one comment on how we prove this. To prove this harder inclusion, that this big product ideal is contained in here, the key point is to show that that this function, which is not rational because this part is the part involving these Puiseux series, but you can still define it to be analytic in a piece of the upper half plane. You can show that this non-rational thing is bounded near 0, 0, and then you get that this times this piece is bounded near 0, 0, and then you get that Z2 plus QJ over that is bounded by 0, 0. And then so you can form like basically what happens is you form a product of all of these different types of things. I can take any combination of these and these up to MJ times, and then you do that for all the different factors. And that's the key point for showing this inclusion. And then again, here's the conjecture, just so people can see it stated isolated. So here's our numerator criterion conjecture. You form this ideal from all that pure stable factorization data. And finally, let me state our evidence, which I think is pretty compelling, but it also, like our proofs, fall short of proving it in general, because there turns out to be like interesting combinatorics going on in some sense in the different ways that these initial segments can overlap with each other. It ends up being the real issue. So here's our evidence. So the conjecture holds in all of these different cases. So you get a characterization of the admissible numerator ideal. So I already stated this is the easy inclusion. If P vanishes to order 1, and that means you have the 0 set of P has a smooth point. If P vanishes to order 2, you can work through it, and you have these two pieces to worry about potentially. I mean, you could have repetition here, but you're looking at this product ideal, and so you have to worry about how these two initial segments overlap with each other, and that and there's something to argue there. But for two of them, it's fine, and like you can work it out. And then it gets harder if you have an arbitrary number of them, but if you assume extra things that make overlapping issues easier, like assuming you have what's called, and this is an term from algebraic curves, an ordinary multiple point. So P vanishing to order M and having M distinct tangents at 0, 0. So that would mean that you have all of these different distinct QJs. You have M of them, and not only are they distinct, but their first derivatives are all distinct. So if you have M distinct tangents, so in that case, it will break up locally into M smooth pieces, but they all have to have distinct tangents, and that makes the combinatorics of the overlapping of these segments simple enough. And then a last case, which is kind of opposite to this one, we can prove it for if you just have these like repeated segments here. So if all of these Q's are the same, you get the conjecture as well. And again, that's just because having them all the same makes the combinatorial issues easier to resolve. And this I already mentioned earlier. You can define this bracket polynomial, which makes many of your questions easier to think about, I suppose, that you can remove Puiseux series with this bracket polynomial. And I think that's all I wanted to say.
But you have photo at the end. Anyway, thank you very much for the very nice talk. And are there any questions? Sorry, one quick thing that I wanted to just check was you said everything for two variables today, but that, yeah.
Yeah, so all the Puiseux series stuff is all two variables. The homogeneous expansion material is D variables.
Right.
That stuff's a little easier, but all the like non-tangential regularity stuff, basically you can do it in D variables using the homogeneous expansion business as the tool. But this more refined material at the end is all two variable.
Yeah. Okay. Professor Singh, yeah, I think you have one more question at least.
Yes, you see, do you have any factorization formula for more variables, like separated variables? Some variables in one factor, other variables in the other factor. Do you have any such factorization formulae?
No, I mean, not something that we've thought about. I mean, obviously, if you could factor it into all
because that is what is the application in an entanglement.
Oh.
I could send my paper to Apurva, he will send it to you. It is in Contemporary Mathematics, volume 687.
Okay, sure.
And did you do this too just for illustration, or you have results for more variables, this factorization that you presented?
So the Puiseux factorization, I should have emphasized, I mean, all that is two variable stuff. So let me go back to
function of one variable, right? In the Weierstrass preparation, at Z2 minus 5, as early as then, I guess. Yeah, yeah.
Yeah, so let's see. So this part here, homogeneous expansion theorem, that works in D variables, and so does this theorem. But then the rest is basically all two variable. And you start to see that so the Weierstrass preparation theorem is fine in D variables, but you can't factor Weierstrass polynomials into into nicer pieces in higher variables. So Puiseux's theorem is also definitely a two-variable thing. I guess people say, well, you'd use some, I don't know, fancy like resolution of singularities as a replacement or something like this, but that's above my pay grade, I guess.
Wonderful talk. Thank you very much.
Oh, thank you.
Any further questions, comments? No, it's the same question. The hand is still. Okay, so yeah, if there are no further questions, let's thank the speaker again, either physically or virtually or something.
Thank you for listening.
Maybe I'll stop the recording.